Everyone, this is Marg, and today I'm going to talk about the quiz for Chapter 32, specifically Problem 3. This problem states a particle with charge minus 5 coulombs initially moves at v equals 1 meter per second in the positive x direction and 7 meters per second in the positive y direction. If it encounters a magnetic field B with a magnitude of 10 teslas in the positive z direction, find the magnetic force vector on the particle. So we know that the magnetic force vector on a moving particle F is equal to Q times V cross B. And if you're like me and you forget cross products and which was it sine or cosine, I have a little like memory hook over here. So the dot product A dot B is equal to the magnitude of A times the magnitude of B cosine of the angle between them. The way I remember this is that the cosine, the O in cosine, looks a lot like the dot in the dot product, and then by process of elimination you can just say, you know, the cross goes with sine. So hopefully that's a useful memory hook. Anyway, so we want to know the magnetic force vector on the particle. We're going to do this by component. The answer choices are by component. We're given the velocity vector in components, so we're going to take this sort of component by component. You see I've written F1 and F2 here. That's because when I do the calculation using V sub x and V sub y, I don't really know for sure which of these force components corresponds to the force in the y direction or the force in the x direction. So we're going to worry about that later. Right now, we just want to know the magnitudes. So we'll say F sub 1 is equal to Q, the charge, times the magnitude of V in the x direction, which is 1, times B, the magnitude of the magnetic field, which is 10, times the angle between them. We see here if V sub x is pointing here and this is B in the positive z direction, we have a 90-degree angle here, so sine of 90. This gives us minus 50. Again, just ignore the sign, doesn't matter here. Then for F sub 2, we're looking at V sub y. We're crossing that with our magnetic field vector. So we've got minus 5 times 7 times 10 times the sine of the angle between them, these two vectors, and that gives us 350. Now we want to know which of these is the x component, which one is the y component, and what are the actual signs. We don't actually know what the signs are from this calculation, even though they do look negative. It's actually, we're just looking at a magnitude. So now we have to apply the right-hand rule. And something to be careful about here is that the particle we're concerned about has a negative charge. And we know that the right-hand rule only works for positive test charges. It only gives us correct answers if we are looking at positive test charges. So when we apply the right-hand rule here, we're going to have to flip our final results. So let's go ahead and do that. We'll start off with V sub x. So I'm going to point the fingers of my right hand in the direction of V sub x, and then I'm going to curl my fingers upward in the direction of B. You'll find if you do this that your thumb is pointing in the minus y direction. Now, because we're dealing with a negative charge, we have to flip this result, and we now know that this is going to be in the positive y direction. So F sub 1, where we used our V sub x over here, we now know that F sub 1 is equal to F sub y. So if we're going to write our final force vector in components here, we know that our y component is positive 50. We'll apply the same reasoning for F sub 2. So I'll point the fingers of my right hand in the direction of V sub y. I'll curl my fingers upward in the direction of B, and I find that my thumb points in the direction of V sub x. But again, I have to flip that result because I'm dealing with a negative test charge, and so I get that my force vector is going to be in the negative x direction. So we have minus 350 for the x component of our force vector, and there we go. We're done.